Example on how to insert numbers into an AVL tree. So I have given a question here, that is insert the numbers 55, 81, 96 etc. up to 40 into an AVL tree. So let's look at the procedure one by one. Okay. So first we have to insert the number 55. So the 55 will be at the root. Okay. And this 55 has a balance factor 0 because it doesn't have a right or left subtree. Then we had to insert the number 81. I'm just writing in 81. So the 55 will be at the root and 81 will go to the right side, that is we have to perform the normal binary search tree insertion. Now this has a balance factor 0 and this has a balance factor -1. The reason for getting this balance factor -1 is this 55 has only one child on the right side, so we have to take the height of the left subtree as -1. The height of this node is also 0, so if you calculate the balance factor -1 minus 0, then this will be equal to -1. So that is why we got the balance factor of the node 55 equal to -1. Now this is an AVL tree, it doesn't violate the condition for an AVL tree. Now we are going to the next insertion, that is we have to insert the number 96. So we have 55 on the root and we have 81 on the right side and we have 96 on the right side of 81. Okay, now if you calculate the balance factor, this is 0, this has a balance factor -1 and this has a balance factor -2. The reason for getting this 55 -2 balance factor is this has a height 0, this has a height 1, and if you look at the height of this left subtree, it will be assigned as -1 because 55 has only one child, that is 81. The height of the other child will be taken as -1 by default. So the height will be -1, that is this -1, and the height of 81 is also 1, so -1 -1 is -2. Okay, so we got the balance factor of this one as -2, so this is a violation for AVL condition. Now we have to take two movements from this node 55 to the newly inserted node 96. So the movement that we should perform is one this way and other one this way. So this is essentially a right movement. So if you have a case where we have the right movement, in order to balance it we had to perform a left rotation. So we have to rotate the number 55 to the left. So when we perform the rotation of 55 to the left, then the 81 will become the root, then 55 will be on the left side of 81. So I will draw that tree here. So we have 81 at the root, and on the left side we have 55, and on the right side we have 96. So now if you recalculate the balance factor, this has a balance factor 0, this has a balance factor 0, and this has a balance factor again 0. Why 0? Because both of them are at the same height, 0 and 0 and 0. You should not confuse with the balance factor that I'm saying and the height I'm saying. You should be able to understand that balance factor and height are different thing. Even if I don't write here, you should remember that I am calculating it in my mind. Okay, now we have to perform the next insertion, that is 36. So if you insert the number 36, I'm writing here, insert the number 36. So 81 will be my root as before. Then I have the left node as 55 and the right node as 96. Okay, now I am going to insert the new node, that is 36. Now if you calculate the balance factor, this has a balance factor 0, this has a balance factor 0, this has a balance factor 1. Why 1?
It's 7:30.
Because this has only one child, so which has a height 0, this 36 has a height 0, and doesn't have a right child, so you take the height of right child equal to -1. So this is actually 0 minus -1 equal to +1. Okay, now the height of this one is 1 and the height of 96 is 0, so the balance factor here will be again 1. So I'm just removing these two. Okay, so this one is not violating the AVL condition because we have all the balance factors within -1, 0 and 1. Now we have to insert this next number, that is 24. So if you insert the number 24, we can see that, so I'm writing here in 24. So the 24 will be on the left side of 81, so I'm writing it here. So I have 81 first, then I have 55, then I have 36, then I'm inserting the new number, that is 24. Okay, now you calculate the balance factor. The balance factor of 24 is 0, this is -1, and this is this is 1. The balance factor of this one is 2. Balance factor here it is 0. Then the balance factor of 81. So if we have height here 2 and we have height here 0, so the balance factor will be again 2 here. Now starting from the bottom side, if you move to the top, you can see that this node 55 is violating the balance factor for the first time if you traverse from the bottom side. So we, starting from this node 55, we are moving to the left by 2 steps to reach the node 24. So the movement that we are making is left. So if you have a left case, left, then you need to perform a right rotation of the node, which is violating the condition. So we are rotating 55 to the right. So if you rotate 55 to the right, the link that is coming to 55 will be now connected to 36. That is the important point that we need to keep in mind. Then this 55 will become a right child of 36. So I am writing it here. So I have the number of 81 as the root as before. Then this 85 is connected to, instead of 55, that will be connected to 36. Now the 36 has a child 24. Now this 55 will be on the right side of 36. Now we have the number 96 on the right. Now this tree and this tree will have the same inner traversal. Okay, so previously it was 24, 36, 55, then 81, then 96. Here also we have 24, 36, 55, 81 and 96, but this is balanced compared to this one. Now if you recalculate the balance factor, we have the balance factor here 0, this one is 0, this one has a balance factor 0, this one has a balance factor 0, and the balance factor of 81 will be now, this 36 has an height 1 minus 0 will be 1. So this is essentially satisfying the AVL condition. Now the next number that we need to insert is 45. So in order to insert 45, we will traverse from the, we insert the number 45. So I'm writing it here. So insert 45. Now you can imagine how, where the number 45 will reach. So I will do it here. So I have the number 81, then I have the number 36, then 24, then 55, then 96. Okay, now if you insert the normal binary search tree insertion, then you can see that the 45 will be on the left side of 81, right side of 55, again on the left side of 55. So this 45 will reach here, so I'm writing 45 here. Okay, now if you recalculate the balance factor here it is 0, here it is 1, here it is 0, here it is again 1, sorry, here it is again -1, here this is 0, then here you have the balance factor, this has a height 2 minus 0, that is 2. Now if you look at this node, you can see that the node 81 is violating the AVL condition. So in order to reach the node 45, we had to make two left movements. Sorry, this is a left movement, and to reach 45 we have to perform another right movement. So this is essentially a LR condition. Okay, so if you have an LR condition, then you have to compensate. If you have an LR condition, you have to compensate it using again L and R. This L go to the R side and this R go to the L side. So we are rotating this 36 to the left first. Okay, if you rotate 36 to the left, what will happen? If you rotate 36 to the left, whatever is connected to 36 will now connected to 55. Okay, so whatever is connected to 36 will be connected to 55, because we are taking 55 as the point, then we are rotating 36 to the left. Now okay, I will draw it here. So I have 81, then I have, instead of 36 I will have 55. On the right side I have 96. Okay, then now whatever is connected to the left of 55 will be now connected to the right of 36. So you have 81 to 55, then you have the number 36, then below that you have the number 24, then you take this 45 from the left of 55, then you connect it to the right of 36. So this is the number 45. Okay, now we have to perform one more operation, that is we have here the left rotation of 81, sorry, the movement to the left, we have a left movement here, so we have to rotate 81 to the right. So we are rotating 81 to the right now. So we can see that this 81 will be rotated to the right and 55 will be the new root now. So we have the new root as 55, and on the right side I have the number 81, and again on the right side I have the number 96, then here I have the number 36, then on the right side I have the number 45, and on the left side I have the number 24. Now if you recalculate the balance factor, all this node will have a balance factor that is allowed in an AVL tree. So this has a balance factor 0, here I have 0, here I have it as 0, this is 0, this is actually -1, and this is also 0. Okay, so this is an AVL tree again. Now let's look at the next number we need to insert, that is the number 87. And if you insert it, 87 will be on the left side of 96. Okay, so I'm drawing it here. So I have the number 55 on the root, then 36, then 24, then on the right side I have 81, then again on the right side of that we have 96, then on the right side of 36 I have the number 45. Okay, this is the tree that we already have. Then we are going to insert the number 87. So if you look at this one, 87 will be on the left of 96. So I am drawing it here, 87. Now you recalculate the balance factor. So this has a balance factor 0. Here I have a balance factor 1. This is minus 2. This is minus 1. This is 0, 0, and 0. You can do the calculation by your own. Okay. Now if you look from the bottom side, this 81 is actually violating the AVL condition. So if the newly inserted node is 87, thus we have to make a right movement first, then a left movement. So the condition case we got here, it is right, left. So in order to compensate that, we had to perform a right rotation here and a left rotation here. Okay, so we'll first consider the right rotation of 96. Okay, we'll first consider the right rotation of 96. So I'll draw it here. Okay, so I have the root of 55. Then I have 36, then 24. On the right side I have 45. On the right side I have 81. Then here 96. Okay, fine. Now if you rotate this 96 to the right, if you rotate the 96 to the right, whichever was there on the left of 96, or this whichever was on the left of 96, that will become the new root. So my new root will be now new root, this the 96, whatever comes to 96 will be replaced by the node 87. So this is coming, 81 is connected to 96, now 81 will be connected to 87. So you can draw it here. I will have 87 here, then on the right side of 87 we will have 96. So this is a result of rotating the node 96 to the right. Now we have one more rotation left, that is we have to rotate the node 81 to the left. So we are rotating node 81 to the left. So whatever is connected to the node 81 will be now connected to 87, and 81 will come on the left side of 87. So I will draw it here. Okay, 1 second, I'll just make a copy of this one. Okay, now we will have to move this 81 to the left. Now if you move the 81 to the left, this 81 will be on the left side of 87, then 87 will be connected to 55 directly. So I have 55 here, then I have 36, then I have 24, then 45. This nodes will not have any change. Then on the right side I have 81. Instead of 81 I will have 87. Then on the left side of 87 I will have 81. On the right side I have 96. Okay, so you can see that this has become a perfectly balanced search tree, right? So this perfectly balanced condition can come in a AVL tree on some cases. It's not always guaranteed. Okay, now we have to insert the next number, that is a number 31. So if you look at this one, 31 will be on the left side of 31 will be on the right side of 24. So I'm drawing it here. I can just draw it here also. Otherwise I will draw it here. You don't need to get confused. Okay, so 55. So we are inserting 31. So 55, 36, 24, 45. Then I have 81, 96. Then I have 87. Okay, 31 will become on the right side of 24. Now if you calculate the balance factor of every node, then this node has a balance factor 0. 31 has a balance factor 0. This has a balance factor -1. This has a balance factor 0. And this has a balance factor again 0. This has a balance factor 0. This has 0. And this has a balance factor 1. And this also has a balance factor 1. You can calculate it by your own. I am not writing the calculation. So this is not actually violating any AVL condition. So this is actually an AVL tree. Now we have to insert the last number as well, that is the number 40. Now if you look at the diagram, the 40 will be coming on the left of 55, on the right of 45, on the left of 45. So I'm drawing that also here. You have 55, then you have 36, here we have 87, okay, and then you have 24, 45, mm, 81, the left, the right I have 96, then on the right I have 31. Then we are inserting the number 40 now, inserting the number 40. So the number 40 will be on the left of 45. Now if you recalculate the balance factor of every node, then we do not have any violation, I guess. So this has a balance factor 0, this has a balance factor 0, this has a balance factor -1, this has a balance factor 1, this is 0, this is 0, this is 0. Then this will be also the height of this one is 2. Oh, sorry, this is not 0. Now this is balance factor 0. This height of this one is 1 and 1, so this will have a balance factor 0 and this will have a balance factor 1, because the height of this one will be 2, the height of this one will be 1, 2 minus 1 will be 1. So we have performed all the operations. So this is essentially a AVL tree after inserting all the numbers that we have given. So I recommend you, if you have confusion in understanding this one, I recommend you to use a pen and paper and draw along the video. Then you can figure out how the operations performed one by one. Thank you.